Chemical Nomenclature, Part 3. Ionic compounds, turning chemical names into formulas. It's going to take practice, practice, practice. So what we're going to do here is go through and practice the explanation that was made in the previous video. If you didn't see Nomenclature, Part 2, that explains how to do this, you should watch that video first. So to turn chemical names into formulas for ionic compounds, we're going to use the crisscross and reduce method. We're going to always write out the ion formulas before we figure out the compound formula. We're going to use parentheses around polyatomic ions whenever we crisscross a subscript and write it outside of those ions. So for example, if you have SO4 and you want to put a number outside of that in a compound formula, we have to put that SO4 in parentheses. And remember that Roman numerals indicate the positive ion charge whenever we see a Roman numeral. So if you see gold Roman numeral 3, that's talking about Au 3+. We can find our ions using this reference sheet. And what we're going to do is practice using this worksheet. And this is called an ion chips worksheet. And these are ion chips. So here's a chip representing a 1+ ion. Here's a chip representing a 2+ ion. Here's a chip representing a 3+ ion. And then we have some negative ion chips as well. We have a 1-, we have a 2-, we have a 3-. I'm going to put a link in the description for how you can make your own ion chips. If you find these useful, you can cut them out of a piece of lined paper, and all you need is a piece of lined paper and some scissors and something to write with, and you can make your own in just about 5 or 10 minutes. You don't really need to use those ion chips, but some people like the manipulative method of learning, and you might find that they're useful for you. They are not required though. I'm going to use them as examples as we go through this. So this is what you should be able to do with this worksheet. For number 1, it says potassium hydroxide. Now the answer is given to you, but let's see how you have to do it here. You take the ion for potassium and the ion for hydroxide and write them down. That's our first step, write the ions. K, potassium, has a 1+ charge, and OH1- is hydroxide. Now remember, that's one of those oddball exceptions, an IDE that's mixed in with the other 8 and 8 ions up here. That's why it has the asterisks by it. So K1+, potassium, is going to combine with OH1- hydroxide. When we do that, crisscross that, we end up with K1OH1, or just KOH. And that's the formula that we see there. So that's what I want you to do. I want you to write the ions out, and I want you to write the formula for the compound. Let's go through and do this left-hand column. In these first 6, we're going to be using potassium. So they're all going to have K1+. Right? Potassium hydroxide, potassium chloride, and so on, all the way down through number 6, they start with potassium. For potassium chloride, we need to find chloride on the ion sheet. Now the IDEs are monatomic negative ions. We can see that chloride would be Cl chlorine with a 1- charge. So when we crisscross K1+ and Cl1-, the 1 goes here and the 1 goes there, we just end up with K1Cl1. Now you can put the 1s in the formula, but you don't have to put the 1s in there. Typically people don't write 1s in formulas, and you just express that as KCl. For number 3, it's potassium oxide. So we're going to take K1+ for potassium. Remember, that's in the K1+ column. And oxygen, when it's a negative ion, becomes oxide, and it's in the 2- column. So we're going to be using O2- there. So crisscross that, and we get K2O1, or just K2O. Again, the 2 goes here, and the 1 goes there, and we drop the plus and minus signs because compounds are always neutral. Now let's take a look at the ones we've done so far with the ion chips. Potassium is a 1+ ion, so I'm going to use a 1+ chip. And hydroxide is a 1- ion, so I'm going to use a 1- chip. And we can see that the peak that represents the plus on the chip and the valley that represents the minus on the chip are all accounted for. They all match up. 1 plus and 1 minus give us a neutral compound, so that's a valid compound formula, one of each. And the same thing works for KCl. A 1 plus combines with a 1 minus. But for K2O, we have 2 1 pluses and 1 2 minus ion, right? There's K1 plus and O2 minus, and the formula says we have 2 Ks, so we have 2 of the 1 pluses, and unwritten 1 O2 minus. All right, so we have 2 1 pluses now for K2, and then O is a 2 minus ion, so now we have 2 valleys there for that 2 minus, and again, the ion chips show us that we have a neutral compound. So if you find it useful to have these manipulatives, go to the link in the description and cut yourself out some from a piece of lined paper. For number 4, potassium sulfate. So again, we have potassium, that's K1 plus. And sulfate has an ATE ending, so we're going to find it here on the ion sheet. Sulfate's right there, SO4 2 minus. So when we crisscross that, we get K2, right? This 2 goes down here. SO4, these are all 1 pluses, so that 1 goes there. And we could say it's SO4 taken once, but we really don't need to write the 1. So if we don't need the 1, we don't need the parentheses. So typically you'll see this written as K2SO4. Now remember that we can only reduce the 1 and the 2, the numbers that we're crisscrossing. The 4 has to be left alone. So we can't reduce 2 and 4 there. So K2SO4. Let's go back to our ion chips. We have 2 K1 pluses. Put them down here. And we have an SO4, one SO4, it's got a 2 minus charge. So when we see K2SO4, we're seeing a compound that's neutral. 2 1 pluses when we have 2 Ks, and 1 SO4 2 minus when we have 1 SO4. For number 5, potassium nitride. K1 plus for potassium. Nitride is N3 minus, right? Nitrogen with a 3 minus charge would be nitride. Remember, the IDEs are the monatomic negative ions that we would find here. So we crisscross this and we get K3. This 3 drops down there, crisscrosses down. The 1 goes there, and 1, or just K3N. So now, if we use ion chips for this example, we have 1, 2, 3 1 plus charges for the 3 K1 pluses, and N3 minus would be a single 3 minus ion. And notice all the peaks and the valleys balance out, and we have a neutral compound. So the chips are showing us that we have a correct formula for K3N. And this last one here for potassium compounds, number 6, is potassium phosphate. Notice we'll be using sodium after that. So for potassium, K1 plus ion, and phosphate is going to be here with the 8s and the ites. There it is, phosphate, PO4 3 minus. So again, you can see that finding the ions is half the battle. Don't try to remember those in your head. Write them out so you can do a visual inspection. So we're going to take the 3 and put it there, and the 1 and put it there, and we get K3 PO4. And if we say taken once, that's fine, but typically people won't do that. They won't use the parentheses, they won't use the 1, and they'll just write K3 PO4. So last time we're going to use the chips here. We have 3 1 pluses combining with PO4 3 minus, and we get a neutral compound if we have 3 Ks and 1 PO4. Again, K is 1 plus, so we have 1 plus 1 plus 1 plus for the 3 Ks. PO4 is 3 minus, so when we have 1 PO4, that's 1 3 minus. Total positive 3 balances total negative 3. All right, Moving down for problems 7 through 14, we can see we're using, actually I guess it's 7 through 12, we're using sodium as the positive ion. So let's get those all set here. Sodium is Na. So for 7, 8, 9, 10, 11, and 12, we're using Na. That's sodium. But it's an ion of sodium. So we have to find sodium, and we see it's on the periodic table here. It's in the 1 plus column. So Na 1 plus. All right, so now we have hydroxide for number 7, sodium hydroxide. Well, there's hydroxide again, right? OH1 minus. We used that one before. OH1 minus. So when we crisscross Na1 and OH1 minus, we get NaOH, one of each. One positive, one negative, neutral compound. If you write it with the OH in parentheses and a 1 on the bottom, and you put a 1 by the sodium, that's technically not wrong, but typically we don't do it that way. We don't put parentheses unless we have to, and we don't put the 1s in there, so we just write it this way as NaOH. All right, for number 8, sodium chloride. So Na1 plus, and again, for all of these, we're going to be using Na1 plus for 7 through 10. Chloride is Cl 1 minus. Chlorine with a negative charge would be chloride. Remember, IDEs indicate monatomic negative ions. Chlorine's in the 1 minus column. Cl 1 minus. So we get NaCl. One of each, one positive, one negative. Number 9, sodium oxide. We've used oxide before. Remember that oxide is O from the 2 minus column. So we get Na2O1, Na2O. 2 1 positives and 1 2 negative. So the charge is balanced. For number 10, sodium sulfate. We've used sulfate before. That's SO4 2 minus. So Na1 plus SO4 2 minus gives us Na2 SO4. If we want to write it as Na2 SO4 taken twice, taken once, we could do that, right? The 2 goes here and the 1 goes there. But again, we typically don't use the 1 and we don't need the parentheses, so we just write it as Na2SO4. Remember, we can only reduce the numbers that we're crisscrossing. The 1 and the 2 could potentially be reduced, although 1 and 2 don't reduce, so we don't bother even doing anything with that. We just write it as Na2SO4. You can't reduce the 2 and the 4 because the 4 is part of what makes it sulfate. That has to stay there. For number 11, sodium nitride would be Na1 plus and N3 minus. And you might remember that we used N3 minus before. That's in the 3 minus column for nitrogen. So when a nitrogen becomes an ion, it forms a 3 minus ion. It's nitride. We get Na3, right? This 3 goes down here. N1. This 1 goes here. Now we typically don't write the 1 in there, so we would just write that as Na3N. And for number 12, sodium phosphate would be Na1 plus, and PO4 3 minus is the phosphate ion. We could find that on here by the 8s and the ites. If we look around here, we can see phosphate is listed right there. And you can see these are alphabetized by the first letter in the formula. So phosphate is PO4 3 minus. So 1 goes there, 3 goes there, and we get Na3PO4. Again, we could write it as PO4 taken once, but typically we see it written as Na3PO4. So there's 3 Na1 pluses and 1 PO4 3 minuses. Let's continue on with this left-hand column here. We're going to pick up the pace a little bit. So now we're on to number 13. These are some calcium compounds. 13, 14, 15, 16, 17, and 18 are all calcium compounds. So let's find calcium and figure out what the ion charge is for it. Calcium is Ca, it's 2+. You'll notice there's no Roman numerals in any of these, so we don't have to worry about looking for any other possible charges for calcium. When there's no Roman numeral, it only has one possible charge. Calcium with no Roman numeral means it's always going to be 2+, since it's in the 2+ column. So again, we had a hydroxide, a chloride, an oxide, a sulfate, a nitrite, and a phosphate. And we did that again, a hydroxide, a chloride, an oxide, a sulfate, a nitrite, and a phosphate. We're going to do that again. A hydroxide, that's OH1-. We've already looked that one up. A chloride, Cl1-. An oxide, an O2-. A sulfate, SO4 2-. A nitride ion is NN3-. And a phosphate ion is PO4 3-. When we crisscross these, we get Ca and then OH taken twice. Now, if you put the 1 there, you can do that, that's fine, but 1 and 2 can't be reduced. And it's really important that you remember to put the OH in parentheses, because CaOH2 is wrong. That means 2 H's, and we need to have 2 OH's. We need to have 2 of that entire negative part. So we have a 2+ and 2 1-. 2+, oops, sorry, we have 1 2+. So we have Ca2+ and 2 OH1-. We don't just have 2 H's, we have 2 OH's. So you have to put the OH in parentheses. All right, for Ca2+ and Cl1- crisscross, we get CaCl2. Ca2+ and O2- initially give us Ca2, this 2 goes here, O2, this 2 goes here, but 2 and 2 reduce, right? You can divide them both by 2, so we should just get CaO for our formula. We should write it that way. Ca2+ and SO4 2-, again, we crisscross the 2's, Ca2, SO4 taken twice, but these 2's can reduce. 2 divided by 2 is 1, 2 divided by 2 is 1, and we get Ca1, SO4 taken once. We don't bother putting parentheses around that, we just write it as CaSO4. So the smallest piece of the calcium sulfate would be 1 Ca with a 2+ and 1 Ca with a 2-. That's what the formula can represent, the smallest piece of that compound. Okay, so Ca2+ and N3- would be Ca3N2, right? This 3 goes here and the 2 goes there. Ca2+ and PO4 3- would be Ca3 PO4 taken twice. So that gets us all the way down through number 18. Let's just take a look at these hydrogen compounds. So number 19, 20, 21, 22, 23, and 24, I'm sorry, up through 23, have to do with compounds that have hydrogen. Now, I just want to make a couple quick points here. We sometimes use nicknames for chemicals. These are called common names. So water is the common name. The systematic name for that, number 19, would be hydrogen hydroxide. So you could call it water. If you call it hydrogen hydroxide, or I guess we'd call it hydrogen oxide, sorry. That would be H1+ for hydrogen, because hydrogen is in the 1+ column. And then oxide would be O2-. So we could write it as H2O. And that's a pretty common formula. I bet most people know that H2O is water. The thing is that when water breaks apart into ions, we don't see it breaking apart into these two ions. If you take water and break it apart into ions, the positive ion is H1+, but the negative ion is actually OH1-. So chemically it makes a little bit more sense to write water as HOH. We still have two hydrogens, right? Two hydrogens, and one oxygen. The charges still balance. So we're going to write water as HOH. Now, a quick note on these other hydrogen compounds. Compounds that begin with hydrogen typically release hydrogen ion when we make solutions with water. And hydrogen ion is very reactive. Remember, a hydrogen atom is only a single proton in the nucleus for the most common hydrogen, and a single electron outside of that nucleus. So when we take that electron away from a hydrogen atom and make it a hydrogen ion, that's a lone proton, and that without any shielding is a very reactive thing. So we take compounds that release hydrogen ions when they go into solution, and we call them acids. So hydrochloric acid is the acid name for this, and the systematic name for hydrochloric acid, if we were to name it as a compound not dissolved in water, would be hydrogen chloride. So if we know it's hydrogen chloride, we can go from there. So that's number 19. Number 20, hydrogen chloride, would be made of hydrogen ion and chloride ion. Again, we're using the same ions that we've used before. Chloride is Cl1-. So when we crisscross this, we get HCl. Now, if you dissolve that in water, we call it hydrochloric acid, but when it's not dissolved in the water, it would just be called hydrogen chloride. For number 21, we have another acid, sulfuric acid. The regular name for that when it's not dissolved in water would be hydrogen sulfate. So hydrogen and then sulfate, right? Hydrogen is H1+, and sulfate is SO4 2-. So crisscross that, we get H2 SO4 taken once, right? The 1 goes there and the 2 goes there. So H2 SO4 taken once. 2 and 1 can't be reduced, and we don't need to write the 1. So we typically write this as H2 SO4 without parentheses. So we can't reduce the 4 from sulfate ever. That wouldn't look like sulfate anymore if we did that. But we can only reduce the numbers, like the 1 and the 2 here, that we're crisscrossing. And since 1 and 2 can't be reduced, we don't reduce them. Don't need the 1, don't need the parentheses. H2SO4. Number 22 is really an oddball example. This is also a chemical that we use with a common name. So number 22, this is one you really just have to memorize. Ammonia is NH3. So how come they have it mixed in with these other chemicals that are starting with hydrogen? Well, consider that if we take H1+, the ion for hydrogen, and we combine it with N3-, the ion for nitride, this looks like it would make H3, right, N1. Crisscross those numbers, the 3 and the 1. Remember, we always drop the plus and the minus signs because compounds are neutral. Well, it turns out that H3N would seem to imply that this is a compound that releases hydrogen ions in solution that behaves like an acid. But in fact, it doesn't do that. And since it doesn't do that, we actually write this formula without putting the positive first. So because the formula is kind of a standout formula that way, we give it a common name and we call it ammonia. And when we get to acid-base chemistry, we'll talk more about why that's important. But that's just a chemical you should memorize. NH3 is ammonia. All right, last one here that starts with hydrogen, number 23. Hydrogen phosphate is another word for another way to describe phosphoric acid. If it's dissolved in water, we call it phosphoric acid. If it's in its dry state without being dissolved in water, we call it hydrogen phosphate. So H1+ for hydrogen. Phosphate is PO4 3-. Once again, H1+. Phosphate would be here by the 8s and the ites, PO4 3-. When we crisscross this, we get H3 PO4. You'll notice that starting at 24 and going down to 29, we have iron 2. Remember that when we say iron 2, we're talking about Fe2 plus ion. Turns out that iron, Fe, could be 2 plus or 3 plus. So we'll be using iron 2 here, Fe2 plus. So you should be able to finish the rest of this worksheet. And once again, if you're interested in making these ion chips, if you think these would be useful for you, you can make a set with a single piece of lined paper, something to write with, and a pair of scissors. Just check that out in the description. All right, good luck.